Test. Test the mic. Test the mic. Test the mic. Test. 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 Test the mic.
La journée quoi aujourd'hui? Ok. On est on ou... Okay. So, okay. So, good morning. morning, everyone. Thank you for joining us to this last session at the Science for Climate Action Pavilion. We hope you enjoyed your COP27. Our session today will be focused on different risks related to climate change, and we will discuss solutions to move towards long-term resilience. So let me first introduce our great scientists and speakers today and their complementary expertise. We have with us this morning Nathalie Ilmy. So Dr. Nathalie Ilmy is researcher at the Scientific Center of Monaco. She is an expert in macroeconomics and international finance. Her field of expertise is environmental economics, and she has several interdisciplinary projects on environmental sciences and economics to better evaluate the socio-economic extent of impact and costs of action versus inaction with regard to carbon emissions. She is lead author for IPCC Special Report, SROCC, and for the AR6. Dr. Christina Tirado von der Pallen. So Dr. Christina Tirado works at the interface between science and policy on climate change, food, One Health, and sustainability, with focus on small islands and arid and semi-arid lands. And she is a senior policy advisor on climate resilience at the World Food Programme and adjunct professor at UCLA. She is lead author of the IPCC AR6, Health and the Desert chapters, and contributor of the Mediterranean, Risk, Food, and other chapters. She is also a lead author for the IPBS. Dr. Tirado is a co-founder and president of the Sustainability Health and Education Foundation for Integrated Climate Resilience Initiative on Sustainability, Health and Education of remote indigenous communities. Christina is a doctor of veterinary medicine, and she has also a PhD degrees in natural resources, environmental sciences, and aquaculture for Cornell University. Dr. Annelise Riles. She is a law professor and an anthropologist. She is executive director of the Buffett Institute for Global Affairs and professor of law, as well as Associate Provost for Global Affairs at Northwestern University. She is an expert in international public and private law. She is the recipient of the Mayer Prize for Lifetime Achievement in the Social Sciences from the Humboldt Foundation. Professor Christophe Danouer, he is a research professor at Université Côte d'Azur. He's a chemical, environmental chemist. He joined the university in 2011 as full professor, and he's working in the Chemical Institute in Nice. His research interests cover environmental and human radiochemistry, looking at the fate and impact of radioisotope on the hydrosphere, biotope, and human. And he is also the director of the Academy of Excellence, Space, Environment, Risk, and Resilience. And finally, Professor Erwin Franquet is a full professor at Université Côte d'Azur, former PhD degree from Université Aix-Marseille, and former professor at Université of Pau. He has his expertise is on civil engineering and smart buildings. He's working in the Polytech department at Université Côte d'Azur, and he's leading also the civil engineering and smart building department. His domain of research concerns the energy management at the buildings and district scales, with a focus toward renewable energy and sustainable transition. Okay, so first let's start with a presentation by Dr. Nathalie Ilmy of the latest IPCC report on the risks due to climate change. So Nathalie, please, you have the floor.
Thank you. I'm very happy to have this last session of the COP with you today, with the University of Nice, our neighbor. And on this pavilion, Science for Climate Action, with the University of Nice, Monaco Scientific Center, IPCC, and of course the Mary Foundation. So I will give you a quick overview of what we had on the risk due to climate change. Recent changes in the climate are widespread, rapid and intensifying and unprecedented in thousands of years. You can see here on this graph that suddenly, after the pre-industrial period, we have this very important increase of temperatures, and we are already at 1.1 degrees Celsius warmer, meaning that to be on 1.5 degrees Celsius, we are really not on the right track. The consequences are highest CO2 concentrations, fattest rates of sea level rise, lowest level in the Arctic sea ice, and unprecedented glaciers retreat. The consequences are clearly extreme heat, heavy rainfall, drought, wild weather, and the ocean is already warming, acidifying, and deoxygenating. Unless there are immediate, rapid, and large-scale reductions in greenhouse gas emissions, limiting warming to 1.5 degrees Celsius will be beyond reach. Now, if we look at the future emissions with different scenarios, only the low and very low CO2 emission scenario can keep us under 2 degrees Celsius or 1.5 degrees Celsius, meaning all the others will not achieve the Paris Agreement. This is very visual. You can see the warming at 1.5 degrees Celsius, 2 degrees Celsius, and 4 degrees Celsius. The changes are really larger. And it is indisputable that human activities are causing climate change, making extreme climate events, including heat waves, heavy rainfall, and drought more frequent and severe. And this is from the Working Group 2 report. Scientific evidence is unequivocal. Climate change is a threat to human well-being and the health of the planet, and it is time for action now. Global warming has caused dangerous and widespread disruption in nature, and climate change is affecting the lives of billions of people despite efforts to adapt. We can see this figure representing the risk with the vulnerability of the ecosystems and the livelihoods. The climate change is impacting not only the ecosystems but also the human systems. Every small increase in warming will result in increased risk. And you can see, this is also visual, you can see the biodiversity loss at 1.5 degrees Celsius, and then at, 3 degrees Celsius. Nature has many services that it renders to the humanity, like pollination, coastal protection, tourism, recreation, food source, health, water filtration. This is seagrass, clean air, and climate regulation. We also have financial constraints. We know that the financial flows going for adaptation are not enough. Most of them go for mitigation, and even those are not enough. we have to close the investment gaps, and for that we need the private sector and the public sector. So the evidence is clear, the time for action is now. Thank you.
Thank you, Nathalie. Thank you. So we have seen that further global warming can only be avoided by addressing the causes of climate change, reducing greenhouse gas emissions and reducing CO2 levels in the atmosphere. And our panelists today will discuss about the risk, of course, but also about mitigation options and strategies to improve energy production and food security, which could contribute to long-term resilience. So we are going to start with Erwin. So Erwin, please, are there any risks for the whole energy system?
So first, before answering, I would like also to thank the Fondation Mary for the occasion to be here with you and to share our ideas. And then the answer to your question is obviously yes, there will be huge risk. I mean, it was clearly said very clearly just before, and it is said since many years, but I mean, we will have, for example, higher climate conditions, which means higher temperature or even cooler winter, which means that our needs of energy, which are already increasing a lot, will be increased a little bit more for, you know, more needs to climatization, air conditioning, or more heating during winter conditions, severe winter conditions. Okay, just to mention these 2 points. Then that also means, as it was said, that we will have more and more disasters, which mean that the distributed energy paradigm that we are building now, so PV and wind turbines mainly, to be very brief, are more, you know, keen to be severely damaged by this kind of disaster that the usual plant that we had in the past. Okay, that means that we could also have, you know, some problem in our energy generation system at some moment, and so we will have to deal possibly with this kind of shortage that could arise because of some damages on our energy system productions. And obviously these damages could also be done on the infrastructure. That means that even if I'm capable to generate the supply, if the supply cannot reach the demands because the infrastructure is not capable anymore, then we can see it could be a problem. And finally, droughtness has also been mentioned. And so it is leading to, it is close to water management issues, but just focusing on the energy point of view, that means that, for instance, one of the main renewable energy available in some country, which is dam hydraulic plants, could not be available anymore because of a low level of water inside these dams, or because of regulation that do not allow you to produce energy to keep the level in the river downward. And this could also possibly be problematic for the management of nuclear power plants, which needs to be cooled down, and so that means that the nuclear power plants must have to be handled with this problematic potential issue. Okay.
Thank you, Erwin. So I understand that nuclear power is a clean option to fossil, but an essential element in the decarbonization of the power sector. But I think we need more scientific evidence that nuclear power is a clean option. So maybe Christophe, how can we better understand nuclear dispersion resiliency with fundamental scientific data?
Yes. Thank you, and again, thank you for the invitation. It is true that actually nuclear power has been discussed a lot in the previous COP and in this COP as well as one of the solutions for clean electrical energy, and also entering the mixed energy So we have seen a lot of options. But it is true as well that we need a lot of scientific input. We know how to run a nuclear power plant. That's not a problem. But in case of an event, a specific event, or an accident, as we've seen in the past, it is true that we need more science in order to understand what is the remediation, what's going to be the migration of the radionuclides that are dispersed in the environment, how would they behave in the environment, and what will be the behavior of the contaminated area. So all of this requires fundamental scientific data from chemistry, from biology, from geochemistry. So we can see that all the fields of science around environmental chemistry, environmental sciences, and also biology are needed in order to better understand what's going to happen if we have an accident or an event.
Okay, thank you. So, and maybe we can go further if there is an accident. Maybe Annelise, how do we handle accident, and is it sufficient?
Well, first of all, thank you so much, Cécile, for organizing, and Sahan and Côte d'Azur. This is really great, and it's wonderful to be and make so many new friends. So maybe it's good to look at accidents that have happened in the past to understand how they've been dealt with so that we can plan for the future. And I should say, I am not anti-nuclear power by any means. I'm just suggesting that as we address the risks that were mentioned, we may have new risks that we're taking on that we need to have solutions for, plan in advance for. So since 1979, we've had 3 major accidents: 3 Mile Island, Chernobyl, and Fukushima. And I would say the kinds of risks associated with those accidents are threefold. First, to the environment. So in the case just of Fukushima, a very, very large portion of the province of Fukushima became uninhabitable and had to be vacated, and the radiation will remain for a very, very long time. The people, the social risk is also very large. People had to be relocated. I think it's an interesting statistic that although no one died from the accident, they had 1,500 people die from mental health emergencies related to the experience of having to leave one's homeland, leave the place where one's ancestors had always lived, leave one's job and community, and move to some other place that you have no connection to, no livelihood, no way of earning money, etc. So 1,500 suicides. And then in addition to that, I think it's important to recognize that there are economic and financial risks. TEPCO, the operator of the plant at Fukushima, was one of the largest, its bonds were held by more people in Japan than any other kind of corporate security in the society. And so the cost of TEPCO going bankrupt would have been borne by everyone in the society. And the cost was very, very large in terms of liability. I believe that TEPCO so far, just before we get to the lawsuits, has paid out $92 billion, US dollars, with a B, in compensation so far. So think about the impact of that on the economy. So the risks are really large. The challenge of this space is that, it's a funny kind of thing, nuclear accidents. They happen very infrequently, and when they happen, the impact is very, very large. And so conceptually, that's very difficult to manage, because by the time an accident happens, most of us have sort of forgotten about the last one. And then it's so large, you kind of start over again and really don't gain much much knowledge from the last one. And we also don't like to talk about accidents. I've been to a lot of panels on nuclear here at this conference, and people talk about the costs and how efficient nuclear energy is, and in not one presentation have I seen anyone internalize the possible cost of an accident when they calculate those prices. But what we know about complex systems from the sociology of technology is that in complex systems, accidents do happen. Whether it's airplanes or any kind of complex systems, accidents happen. And so we just need to plan for those and recognize that that is just part of it. And the problem is that our legal systems, and I can talk more about this later, but our legal systems are really not set up. They're very antiquated, and they do not provide sufficient compensation based on those accidents that we've seen. So for example, in the United States, the Price-Anderson Act limits total liability to $560 million. Beyond that, the government won't pay, the industry won't pay, citizens are on their own. And notice, 560 million, but the compensation from Fukushima was 92 billion. So it gives you a sense of how much extra cost of a large accident would be borne by ordinary people. So we have a lot of work to do to try to create a system that's just and really anticipatory of the reality if we want to use this technology so that it's fairly operated. And I'll just say one last thing, because there's been a lot of talk about inequality at COP, that most nuclear reactors are located in relatively economically disadvantaged communities. They tend to be rural communities, they tend to be impoverished communities, and so they receive benefits from the industry to have those plants in their communities, but whether or not the community really understands the risk it's taking on is a question. So I think we have some work to do also in that space.
Thank you, Annelise. I would like to come back a little bit on water management because several low-carbon energy systems require water. So Erwin, could you tell us what are the issues regarding water management and availability?
Yeah, of course. Or maybe not all of them, but some of them. So first, I would like to speak about water as a resource. So, I mean, once again, we've got some evidence of what will happen or could happen, depending on if you're pessimistic or optimistic. But first, there is clearly a depleting of the resource water, being the surface or groundwater resources, which means that the probability of a lack of water is very important. And so it has to be considered for the impact on the agriculture or on every use of water we can have in the different countries. Another important issue is linked to wastewater treatment. I mean, we could face some issues which are clearly well known, than when you do not have the possibility to treat your wastewater, then I mean, many illnesses could appear very, very quickly, and the quality of life is clearly not the same. Okay? So that's here the main point concerning water as a resource. Then my second point would be water as a flow. And then, once again, flood has been mentioned. And so we are more and more pronounced to know severe flood more frequently. And on the same time, we are artificializing more and more land, even if there are, tendency to try to limit that. But, I mean, the point is there. Where the land use is increasing a lot. And so that means that we do not have the water sink, the natural water sink that were available. And in addition to that, we also know, for example, in France, there are some researchers and evidence that many trees or many forests that we have now could possibly die in the future because the trees that were there, we will not be able to survive a high temperature. However, this forest or the tree in general, they are very useful to keep the ground as it is and to stabilize the ground. So that, I mean, there are mechanical effects, and the way that they are leading the water could be clearly modified, and that means that water could be and could go almost everywhere. I mean, there is no natural mechanical system to constrain its flow. Okay, so that was these 2 points. First for the resources, and then for the risk of impact.
Thank you, Erwin. So, because the water, energy, and food sectors are strongly interdependent in that both food and energy sectors require water, and the food and water sectors require energy. So climate risks in one sector can create risks in the other two sectors, with additional knock-on effects in other sectors, such as health. And Christina, what are the risk issues regarding the food sector? What are the main risks you can identify in relation to food systems and food security?
Thank you so much for the question and for including this important topic in the panel. So the main risks depend very much of the socioeconomic determinants and the geographical situation. So I will separate them in two aspects. So first, the main risks that we are seeing, climate change systemic risks and food crises that are becoming increasingly complex because we are having multiple climate hazards that occur simultaneously or very quickly, one after the other. For example, all the issues that we are seeing about intense droughts, they are followed by intense floods, and they are concentrating and dispersing contaminants, for example, in a way that we have not seen before. And we have also multiple climatic and non-climatic risks that are interacting. So what we are seeing is compounding and cascading risks across sectors and regions that eventually are leading to large world food crises. If we put this together with crises like the one of war in Ukraine and limits to exporting and humanitarian aid, this is a total disaster by itself, and this is a huge risk that we are seeing. So this is impacting acute food insecurity and acute malnutrition, which is not just the typical indicator that you know from the Food and Agriculture Organization. We are talking about starving and famines. We are talking about early alert crisis for crisis about 3 in the IPC classification. If you don't act immediately, urgently, these populations, and mostly children, will die. So this has been forgotten and something that is missing in the IPCC for the reason that this is new. These indicators are new, and also because probably scientists have to learn more about humanitarian crisis and what implies resilience. First is to save lives. So this link needs to be done because there are a lot of observed data. The observed data during the last 5 years of research, in between 2015 and 19, they were an estimated 166 million people in 26 countries, mostly in the Horn of Africa, East Africa, and the dry corridor in Central America, that require humanitarian assistance to save their lives due to this climate food crisis. Now, the idea of thinking that these risks are expected to increase with further warming, this is leading to increases humanitarian assistance that the world will not be able to respond to. So after, in the second part, we will discuss how we manage these risks. But coming back to high-income countries, the main worry and concern is basically that climate change and variability is leading to the emergence of new food safety risks that are also compounded and cascading. And they are related to higher CO2, to driving emerging risks that are in the oceans, for example, everything related to algal, harmful algal blooms, or in land territories, it's related to an increase of frequency and change of range, geographical range of mycotoxins. There are also infectious diseases, but those are, like more, I think, more easily to prevent and to have under control with alert systems. So thank you.
Thank you, Christina. So now we have good ideas about the risks, but as scientists, we need to share solutions with all stakeholders and policymakers to ensure long-term resilience. So first, Christophe, could you tell us what's the role of scientific transdisciplinarity to build resiliency strategies?
Yes, I can say a word about that. Actually, at University Côte d'Azur has created a very original structure, which are called academies. And so usually at the university we have disciplinary structures that are very vertical, and that's perfectly fine. And so at University Côte d'Azur we've created transversal tools that are kind of laboratory without walls. So they are virtual institutes, actually. That's maybe the best way to describe them. And so we have 5 of them, and in one of them we do address the question of environment, risk, resilience, and societies, which means that we are looking at all kinds of risks related to the environment and impact on societies. Societies in a political sense of view, that means the organization of people, and how risk can disturb this organization. And so one of the best ways to address this point is really to look at transdisciplinarity. So transdisciplinarity is a key word right now. I mean, it's used everywhere. But we have to understand that it's very difficult to do, actually. It's very difficult to implement, and that's why we try to foster this transdisciplinarity, to try to have people who will never talk to each other create new projects. Usually a geochemist or a chemist or a biologist will never talk to a lawyer or will never talk to an economist. First of all, because they don't understand each other, and second, because they don't have any interest to do that. Other from pure intellectual interest. And this is what we try to modify. This is what we try to foster, with money, of course, because we think that the risk is not a disciplinary problem. Risk is an interdisciplinary problem, as we've heard already. And has consequences in all kinds of fields of science, natural sciences, but also human sciences, social sciences, etc. So we think we really need to light the problem for different perspectives, and we think that we need all the field of sciences from a broad perspective to understand those type of questions, and that's what we are trying to do.
Thank you, Christophe. So coming back to our subjects, and for example, we will start with the energy. Erwin, what would be the sustainable solutions to tackle energy problems?
I'm not sure. So thank you for this question, which is very difficult, because first I would say I'm not sure there is one solution. So the solution is difficult to find. The reason behind that is that, I mean, with distributed solution and renewable energy, which, I mean, the intermittency is known. I mean, the local conditions are more and more important. I mean, this is also what we have to keep in mind. I mean, fossil fuel was the age of facility. I mean, it was easy to handle. We can put that on the moon, and maybe not on the moon, but I mean, it is working the same way everywhere. I mean, and you can handle that very easily. Okay, and the energy density was huge. So, I mean, that's why it's so difficult then to eliminate them, even if we have to. Okay. So here again, I would say that in the same idea, I mean, first we have to have an holistic point of view, and first at the technological level. I mean, we have a need of energy, and this need of energy is a need of to summarize, of electricity, heat, and cooling. Okay. So as it is done in Europe, I mean, we have to think, you know, on flexible systems that can provide, I mean, the type of energy you need at the moment you need, and not necessarily one single solution, which is not very efficient. Then obviously we can transform, there is conversion technologies, but it's not efficient. I mean, this is a smart way of dealing with energy system, just relying on an intelligent, you know, thinking of our needs and our use of the energy. Then here, so we are working a lot, obviously, on the supply side. I mean, putting more renewable energy, having more flexibility and intelligence on the system, as I was just saying. But we also have to work on the demand side. And for instance, personally, this is the type of research I'm doing with other people in Université Côte d'Azur and around the world. I mean, but the demand side management is also, I mean, there are leverage action here that can really ease, you know, our way to a sustainable future. I mean, to better, you know, instead of more supply, we can work on the demand, and this can be done on the energy system, but that can be, you know, transferred to mobility and to other points. So that was just for the technical point of view. And then my point would be, once again, to have an holistic approach, but more general, considering law, economy, and social sciences, because, I mean, all the studies on rebound effects or you know, optimus bias from psychology have shown that technical only solutions are always not working very well. So even if I'm a physicist, I mean, if I'm thinking of efficiency of the system as an engineer, which I'm also, I mean, I have to consider that. Okay, so that means that beyond all these technical points I've mentioned, we have to involve more the people and to better know how people will react to a new technical solution or a new way to deal with the demand, depending on their cultural, historical, and local traditions, law, and so on. Okay, it will not work the same everywhere in the world. Okay, so I would say, once again, general approach, general point of view, are trying to, and an holistic approach, both from technical side, but also combining all the sciences we know now on this topic. Okay. Thank you.
Thank you. So if we want to dive in a little bit more about, for example, nuclear accident, Annelise, what are some of the barriers and challenges to achieving solutions about nuclear accident?
Okay, there we go. Some of the, well, some of the barriers. Well, I think that I just want to pick up on this point that's been mentioned about interdisciplinarity. I think it's so important, and what you're doing, Côte d'Azur, sounds so exciting. So congratulations, I want to learn more about it. We found with our project on nuclear that in addition to needing all the disciplines, the anthropologists who work with fishing communities, the lawyers who work with the financial markets, the scientists, we also need different sectors of civil society, and universities can be platforms for bringing those people together. For example, in the space of nuclear regulation, the activists who are anti-nuclear and the finance people who fund nuclear power plants all have an interest in the proper pricing of the risk. So they can actually connect, not agree about everything else, but be interested in that piece. And so we can find these nodes where we don't have to agree about everything, but we can at least have a discussion about some specific issues. I think that one of the biggest challenges, you asked about barriers, one of the biggest challenges is that to this interdisciplinary point, the questions are both very, very technical and very, very political, which means that the engineers and scientists don't own them completely. They don't have a right to make the distributive political decisions. Those belong to civil society. But then ordinary citizens don't always understand the scientific and technical piece. And so I think one of the biggest next step challenges, and I really don't quite have a solution, but I know we as universities need to work on it, is how do we create a viable system for civil society and experts to come together and discuss these issues where they each have a legitimate right in a democratic process to have a voice and different pieces of expertise, but they don't necessarily understand each other. And that seems like a big challenge.
That's a big one. Thank you. And finally, Christina, which approaches can we use to prevent climate risks to food insecurity and malnutrition?
Thank you for the question. So they are the way that has been dealt or successful approaches that we have seen are complex because systemic food risk and food risk management requires investing in very large scale complementary actions that include, on one side, anticipatory actions. And these multi-risk and early warning systems, they have to be implemented across all food sectors, and which is quite involving if you think of all the broad scope of agriculture and fisheries. So to have this and to manage these multiple climate risks from production to consumption, because we are talking through the whole food system, right? There is the multi-risk early warning systems that are supported by digital platforms, and they are linked to contingency planning, anticipatory action, emergency response. Many times in some countries they are also linked with disaster risk reduction. So they are including, in order to be effective and feasible to prevent food insecurity and nutrition, they have to be nutrition sensitive and nutrition shock responsive. So, you know, this is a specific definition that is being used in the field of food security. So these anticipatory actions, basically what are short-term disaster risk management interventions that are implemented between the critical time that you have a rapid alert, and usually 6 months, right? When you have an early warning trigger, and the time that is likely to occur the shock, okay? So this is in the near future, and the natural occurrence of the shock, likely if you have 6 months, you can prepare. If you have less, you can't. I mean, it's like all the pledges for humanitarian aid and for food aid, it does not arrive, does not reach. So these anticipatory actions are protecting food security, they contribute to resilience, and definitely they save costs. So to give you some idea of the savings, the World Bank was estimating that the potential benefits of upgrading these early warning systems and capacity, it could be saved first about 25,000 lives per year, and between 300 million to 2 billion per year of avoided assets losses due to disaster and crisis. So this investment is worthwhile. The way that we are seeing this is that we really need a change on thinking from managing risk and response to managing the disaster risk, which is fundamental, a shift to ensure resilient food systems and communities that do not fall into the dependence of humanitarian assistance after shock after shock. So yeah, I think I leave it here, and yeah, thanks a lot for the question.
Thank you. Natalie, you want to add something? Or?
No, I was just looking at what is happening now at this COP, and they acknowledge urgent and immediate need for new additional predictable and adequate financial resources to assist developing countries. So because we know that we have economic and non-economic loss and damages, so this is something good. The problem is that they have several options yet, and they don't know if they will create a fund or wait for the COP28, and it is on the negotiation now.
Thank you so much. So thank you. I think we can thank all the speakers and all the panelists for these inspiring discussions. So first, thank you. And we have some time to take questions from the audience, if there is some. So please.
Thank you. I am Dr. Atri from India, National Meteorological Services. I think today is now coming to the end of this important COP27, and lots of things have been discussed, and particularly mitigation. Once we are discussing, people are talking on non-conventional energy, wind, power, nuclear, we have just heard. What you see the potential of green hydrogen. People are talking lots on that. This is the future fuel, and we should put more emphasis on green hydrogen. I'd like to have your views on that. Thank you.
First, okay, thank you for this interesting question. But did you see yesterday? I think yesterday there was a specific event on green hydrogen. Yeah, okay. Did you see it? Okay. So I mean, the main figures that I will reuse from this panel. What that I mean, we will do more green hydrogen for sure. However, it is important to think that we have to pay attention not to rely too much on this, because further costs are still expensive, and I mean we've got only 30 years to act, and so that would be difficult to have cost effectiveness so quickly. Regarding the past evidence we have on the development of technology, even if we are increasing the rates of the decrease of cost. First, and also our needs are going to increase so much that it would be impossible to answer all our demand only relying on green hydrogen, even if it was not so costly. So the idea is to use green hydrogen or hydrogen where it can easily replace fossil fuels, and there is no other way to do that. So to give you a specific example, for instance, even if we are going to do that, but we know how to do light electric vehicles, so we can do light hydrogen vehicles, obviously, but for instance, for trucks or for large means of transport, it is more difficult to replace to substitute fossil fuels. Here, hydrogen could be very useful. Okay. There are also, I mean, the main question, for instance, or it's not completely related to energy, but it's the use in cemetery. Nowadays, when we are making cement, we are using fossil fuel first. I mean, to have the heat, to initiate the reaction, and so here we could replace, obviously, by renewable energy, but the chemical reaction currently is naturally, even if you were using renewable energy to have this heat, the chemical reaction is naturally producing CO2. Okay, so it is CO2 emissive. If we were to replace, and it is known, if we were to replace this reaction by another reaction that is also available, we could avoid to produce CO2 and to have water, H2SO, produced by using hydrogen instead of the current situation. So here, green hydrogen, okay, is very useful because this is the only known way to substitute our fossil use and the CO2 emission associated, and there is no other possibility. So clearly, it is a good idea here to have green hydrogen. And green hydrogen, okay, or purple hydrogen, if you do agree on nuclear power plant, but clearly not gray hydrogen, okay? Substituting, okay, just to be sure that for green hydrogen. So, in such cases, it is a very good idea because there is no other way to substitute our fossil, use. And in some other, it can be interesting. Obviously, we have to do that, but we have to keep in mind what I said at the beginning concerning the cost and the development of this technology. Okay, you're welcome. Maybe from the economical point of view, yeah.
No, maybe from IPCC point of view, because we said that in the report that hydrogen is mainly for aviation and shipping. So, yeah, it's maybe not for to replace the electrical vehicle in the street.
Good morning, everyone. I am Jean-Christophe Martin, Professor of International Law in Université Côte d'Azur. First of all, I would like to thank all the presenters for their clear and stimulating presentations. I have a question about nuclear power plants, let's say, and in the context of adaptation to climate change. I do not know anything in this field, so this is a question of curiosity, but I wonder to what extent, on the technological plane, let's say, the nuclear sector, nuclear industry sector, search technical solution to adapt to climate change. Is it requested? Are there technical solutions? And for instance, we have heard about a new trend of designing small nuclear power reactors. Is it an example of such a technical adaptation to climate change or not at all? And if not, are there other solutions that are being researched, I would say? This is probably for Christophe or Erwin.
So I think we all have a lot to say about this. So the small modular reactors, SMRs, you're talking about. So the chief benefit of the SMRs is that they are cheaper to produce because they can be mass produced, kind of like a car at a factory. So that's important to understand. What is the benefit of the SMR? The real benefit is on the production side in the cost for producers. It's not so much about the energy. So, but what's interesting about your question is that the risks of SMRs are completely different. They are they're smaller, so we're not going to see a Fukushima-size accident probably. They're smaller, but they're meant to be placed in much more urban areas. So you can imagine one being placed, they talk about next to a hospital, to run the hospital if it's off the grid, or, in very highly populated areas. And so one of the effects here is that the laws that we have to regulate nuclear power are imagining a catastrophic risk. But what we're going to see more is going to be like a big car accident, like lots of these happening all over the place in smaller quantities. And we probably need a completely different insurance regime and a completely different regulatory regime to take into account these. And the other thing that I'll add is that this is a huge export industry for France, the US, and a couple of other countries, China. And so the challenge of, at an international law level, the IAEA, the OECD regime, completely absolves the manufacturer of any liability. And so as these things are going to be put in Africa and Southeast Asia and elsewhere, the United States producer will have zero liability if something goes wrong, and it will all be on the local energy producer who may not have the ability to do that. So I think that there is a need to adjust the international law around liability if we're going to have this be a major export industry for the first world to the developing world? Yes.
Yeah, maybe I can add 2 points. Well, I'm not a nuclear engineer, but I can try to answer your questions. On the SMR, just to go on with your remark, the other point with SMR is they are geopolitically safe. That means there are no proliferant. And that's the main point, actually. Because one of the major issue is with large reactors is that in a reactor you produce plutonium. And so you could use this plutonium, and only a few countries are allowed to produce plutonium. So the SMR would be is also a control on the use of the nuclear reactors. But that's another subject. To come back to your questions, right now we are relying on the uranium cycle. So we mine uranium, and we use it to put it as a fuel in the reactor. Sometimes with plutonium, it depends where. Some countries are using thorium as well, but and so we have a half open cycles. It depends on the countries. In France, for instance, we recycle the uranium and the plutonium. But the next generation of reactor or the next generation would be designed to burn plutonium. So we have a lot of plutoniums, and so with fast neutron reactor we could burn plutonium. And so that gives another step to the limit of mining uranium, schematically.
Thank you very much. May I add something in my question? For instance, I had in mind through asking this question of new small reactors, I suppose that it changes also the needs about water management, because water is needed to cool down the reactor. So for instance, if we spread this kind of small reactors, will it change the way we have to manage water, fresh water, etc.? Is it something that engineers, scientists think about when they design this kind of technical tools? Is it thus a solution to climate change or not?
Well, yeah, engineers do think about such things, but you can use other coolants than water as well. You have other reactors that use other coolants. Maybe you can add on that, but you have water, but you have also other type of coolants. So there are, from the engineering point of view, there are lots of solutions. But then the question is political and economical.
Hi, thank you for these comments and for the questions. And I think that probably I am the only voice here talking about public health or equity, or perhaps I don't see very well how this fits in the circular bioeconomy, or all the farm to fork approach with the Green Deal. I am just wondering how you see all this impacting the importing countries. I mean, I have seen all the devastation from many nuclear impacts. In Belarus, I have been working for years and years with the World Health Organization, with all the former Soviet Union. Not only that, but also with all the people affected and all the residues. I mean, there are hot spots of incredible high radioactivity in the world that we are not familiar with them. In the Aral Sea, in Kosovo, because they were using dirty bombs. And I would like this maybe to put sometimes also, not in the economic and energetic point of view, but thinking in one health, planetary health, and yeah, to bring this also into the conversation because it's really relevant, particularly for low-income countries that definitely do not have the means to test or monitor contamination. I mean, I have been working with the International Atomic Energy all the time, doing partnerships with them, because the countries that we work in public health, they don't have the capability to detect radiation. And in any market that you find, like farmers markets or just gatherers, all the gathering of strawberries, all the mushrooms, all the poorest people are living from this or complement this diet with wild foods that are contaminated for so many years. So this has to be put into perspective and in global policies and, as you were saying, liabilities, but it will be better not to arrive to the liability, right, but to the prevention. I leave it here. Thank you.
Yeah, I think that's a really good point, that there isn't a lot of talk about the global dimension of these technologies, right? I mean, in the case of Fukushima, the plant was built by an American company. The plutonium came from Africa. I mean, the uranium came from Africa. The nuclear radiation went to Korea and all over the Pacific region, and yet we have mainly national legal regimes to take care of these things and regulate them. And it's very hard under the laws of most countries to come, say, from Korea to Japan to bring a lawsuit. It's very difficult. So we need to change that, because if, let's say, let's imagine the United States exports this technology to Africa, and African people want to come and sue the manufacturer in the United States, it's very difficult to do that. So, and the other thing is that we have an international regime, a patchwork of two different international regimes, one run by the OECD, one by the IAEA. They don't really talk to each other. Different countries are in each one. And many countries who are building nuclear plants now are not in either of these regimes. For example, Korea, China are not in either one, even though they have so many nuclear power plants. At the time of the accident in Fukushima, even Japan wasn't in any of these. And so we have a lot of work to do at the international law level also.
If I can add one thing, it's not only the liability, it's that the residues where they get buried, they stay forever. So the poorest countries are the countries that are offering space to bury these residues. And think, for example, when we saw the disaster of the Aral Sea, which was a mix of misused irrigation with variability and desertification, but misused irrigation. You cannot imagine the hot spots that we could find that were protected by water, so people could not reach them, and suddenly we were reaching areas that were having residues. So a complete change of, we have to think in a planet, not just in something little that may happen close to us or liability, but a complete shift of waters, up, down, concentration, dispersion, what I mentioned at the beginning. We have to think about where we put these residues, because they are forever. And the communities that I have been most affected are really poor. And they cannot monitor. That's the most important thing. So this has to be put in the equation. Yeah, thank you.
Yeah, just a word. I think it's difficult to answer directly to those type of questions, but coming back to my first remark, I would like to underline the real need for scientific data, scientific input with fundamental data to try to understand at the end of the at the end of the chain to answer those questions. But real scientific data to understand the fundamental behavior in the environment and, well, a lot of things are really important to try to answer those questions.
Okay, so thank you for all these inspiring discussions. So I'm afraid we have to close the session. I don't know if there is another question? No. Okay. So thank you so much. So we are keeping that we need more data, we need more information about all these risks and of course solutions. We have to work together, we have to make transdisciplinary research and to provide knowledge and solution to all stakeholders and policymakers. So thank you of all of you for your input and your participation at this session. Thank you for all the public here, and so I am happy now to close the session. Thank you.
Here. Is this presentation? You have 6 presentations. And who will be here? Okay, you will be here? Okay. This one? So there's this one. This one. Is there other ones? Okay, so let me do something. Because if you keep it on the drive, then when you